So welcome to our second discussion of the electrophysiology of cardiac cells. In the first movie we talked about pacemakers, so in this movie we're going to talk about the contracting myocytes, specifically the cells in the atrium and the ventricle that are going to depolarize and contract. And just like before, we're going to be talking about the flow of ions into or out of the cell. So again, a flow is a current, so big I for talking about, because we're talking about a current, and we could be talking about a current for sodium, a current for potassium, or a current of calcium. And in fact, when we're talking about these contracting cells, we will be talking about INA, IK, and ICA. Now, you might notice that on these cells there actually is a little bit of difference between the trace or electrophysiological activity in the cardiac myocytes of the atrium and the ventricle. And this is because we're going to be grossly simplifying what happens. I'm going to focus on three currents, but you can see from this chart there are actually multiple currents that are going on in both these cells. And because some of these currents are different between these two cells, so for example here we have this GERK4, right, that's found in the atrial muscle but not in the ventricular muscle. This means that these cells do have subtly different electrophysiological properties. So what I'm going to do is discuss the properties that we would observe mostly in the ventricular muscle. The same properties are very similar in the atrium, but with a few changes because we have extra currents. And again, even what I'm going to talk about in the ventricle is an oversimplification of what's actually happening. So just like when we talked about pacemaker, we're going to have three currents. However, we're only going to have one threshold. And so what's going to happen is this cell is going to be sort of hanging around at some sort of resting membrane potential. It is going to start depolarizing because an electrical charge arrives from the network. Right? It's connected, remember, to Purkinje fibers, which are connected to AV node, which are connected to SA node. And so when the SA node generates an action potential, that action potential eventually arrives in this contracting myocyte and causes the cell to become a little positive. And at that point, once we reach threshold, we are going to open up a voltage-gated sodium channel, which is carrying a sodium current. So sodium will enter the cell, and the cell will become very positive. And so this is INA. Then, at some point, that INA current is going to inactivate. And as it inactivates, the cell starts becoming a little negative. But we start to quickly flatten out because we start a second current. So this is another voltage-gated channel. It started to open up here, but it's a little bit slow, so it finally opens up here. And what it's going to do is it's going to allow the flow of calcium into this cell. Now this calcium channel is a little bit unusual because most calcium channels are going to be open for a very short period of time. In fact, most channels in general are only going to stay open at most from 10 to 40 milliseconds. This channel stays open for, in the ventricular muscle, it's going to stay open for something like 200 milliseconds. So that's a little bit unusual. And what it means is that the cell is going to be depolarized for a very long period of time compared to most cells that are electrically active. And during that entire time, calcium is going to be floating into the cell. Because it's so unusual, this calcium channel has its own little name. It's called the L-type calcium channel, where the L means long. So long type calcium channel, it's open a long time. During this entire time, calcium is streaming into the cell. Of course, it does eventually deactivate. And once it deactivates, another current takes over, and that is that a voltage-gated potassium channel finally opens, letting potassium out of the cell, and the cell starts to become negative. And so this is the IK. And so notice that at the very end of this, we return to the resting membrane potential. In order to start this again, we actually have to have another depolarizing event arrive from the network, causing us to trigger these three steps again. So a few things that make this electrophysiological trace unique, right, is the nice little cowlick that we have here at the top, which is caused by the sodium channel inactivating, cell becoming a little bit negative, but then the potassium stopping it from going back to the baseline. This very, very long plateau in which calcium is streaming into the cell, causing the cell to become positive. Now, there's another practical implication of this plateau. This calcium is changing the cell electrically, but it's also helping drive the contraction of the muscle. Because some of this calcium that's coming in is going to bind directly to troponin, allowing actin and myosin to start interacting with each other. And some of the calcium that's coming in is going to start interacting with the ryanodine receptor in a process that is known as calcium-mediated calcium release. Because when it activates the ryanodine receptor allows calcium out of the sarcoplasmic reticulum into the muscle fiber, or should I say into the muscle cell, allowing that muscle cell to contract with more force, right? So if we think about this, about 20% of muscle contraction comes directly from the calcium coming into the cell. About 80% of it comes from calcium that is released from the sarcoplasmic reticulum. But why was it released from the sarcoplasmic reticulum? It's because of this calcium here. So this calcium is in fact crucial for the contraction of cardiac myocytes.